Okay, I promised to talk about the starter, and finally to the point where I think I have it licked, and I can show you what I've been doing. So, this engine, Rolls-Royce Viper 102, the starter motor on it is not attached to the engine. It's not a piece of engine hardware. It's airframe hardware. So, it connects through the nose, the inlet of the engine, via, I think, a drive shaft, and the starter is located on a gear reduction box. Gear reduction box also has, I think, hydraulics, for control surfaces of a plane, things like that. Possibly also a generator, or it may be an integrated starter generator. Either way, I'm not sure. Never seen it, never gonna see it, don't have it. So we got to mount a starter on it. These engines, typically you'll have to engage the starter for 20, 30 seconds, even more, to get it up to speed to where you can start introducing fuel and fire, and then you even after the engine is started, you still have to continue to motor the engine with the starter to help keep it going up up to self-sustaining speed. The gas turbine engine has a kind of a danger zone of temperature that, unless you've got a lot of air moving through the engine, which cools it, you can overtemp components in the engine, most notably the turbine wheel in the back. So you can do what's called a hung start or a hot start, where the engine will kind of stop producing enough RPM. It'll stop accelerating through the RPM, and then you're really in danger of overtemping the engine. So starting, very important. Aircraft starters, I don't know much about them. Gas turbine starters, other than that they're crazy expensive, and so therefore, no, not going to do that. I don't have the budget to play around with trying to get an actual gas turbine starter to do it. So, what do we have instead? We have a Delco Remy 41MT style starter. So, this is the starter you would find on a big truck. So, starter motor portion, solenoid enclosure, solenoid, and then it terminates right here, and normally there would be kind of a, your traditional starter nose kind of thing, and a pinion and all that kind of stuff. We didn't want the pinion this kind of stuff, and I had to adapt it to what the engine has. So the engine is an internal spline. It's about 1.25 inches nominal diameter. I think it's 42 splines, so it's a lot of splines. So what I did was, on my CNC lathe, I produced this bar here. So this is the 1.25 diameter. Turned it down, bored it. That was a real pain. And finished the end of it how I wanted. And then I sent this off to be splined. I sent it to a place called Mosier Engineering. They do a lot of high performance domestic car axle kind of stuff. I've had them respline stuff for me before. It takes special equipment. I just don't have it. Not worth the time to try to index and do it on the mill or anything like that. So I asked them to produce it in kind of a loose sliding fit. Generally with internal and external splines, the external splines are easier to produce. So we made the external splines to fit. So I'm sure they kind of did a pass and tested it. I sent them the adapter to make sure it fits. Why did I have it double-ended? Well, I didn't know if they were going to get it in the first shot. I didn't know if I was going to screw the first one up. So I made two shafts like this, sent them out. They splined all the ends, except one end, which I broke off a carbide drill bit in the center. So out of 4 attempts, I had 3 good ends I sent them. So when they sent it back, this one right here, I parted off with the lathe, and we got that on there. So this piece right here that slides, this is the original piece from the starter. This shaft, which is attached to the motor armature, has a straight spline on it. That's what this engages into. See, I can't turn that. It will turn this starter shaft. If I pull it kind of past, I can't even get it faster anymore. This kind of angled spline here normally operated the Bendix clutch on the original starter. I bought this starter motor, you know, it was from a big truck or something like that. The interesting thing about this starter here is it is counterclockwise rotation. It is opposite of what most normal internal combustion engines spin. That's just a function of what the engine needs. This engine, you know, when I spun the wheels, okay, it goes this way, so I figured out that this needed to be a counterclockwise rotation. That made my starter choices much smaller. So very few counterclockwise starters out there. So this shaft I took out, started that as a base. I made this piece. This is just some 12L14 steel or something like that. It's just got a little kind of fork section to engage the I call it throw-out bearing that the starter solenoid engages. So when the starter solenoid pulls that out, it goes and engages that hopefully into my spline section, and also within the solenoid has the contacts in it to spin the starter motor. So interesting thing about this is it has what they call positive engagement or something like that. But long story short is, if this solenoid pulls it out and this binds up on something, doesn't engage, the motor will not spin. The motor does not spin until the solenoid has pulled it all the way out, and then it has kind of a little extra spring that it pulls against, pulls the contacts together, boom, starter motor engages. So you don't have to worry about it kind of starting to spin and then bouncing along on the teeth trying to engage. The only thing is, since this does not have any curved splines like a Bendix, it does not do this as it comes out, which helps you engage into the teeth. So, you know, it could get a situation where this is just going to bang and just stop against the internal splines in there. So hopefully that won't happen. If that seems to be an issue, I may have to file down the ends of all these teeth, kind of point them a little bit to get them kind of find their way. I may do that anyway. Another something interesting to note here is that this shaft was hardened already, so it's hard as hell. You know, it's probably like 60 Rockwell or something like that, so can't even nick it with a file. And then this piece here is made out of a material called stress proof. It's kind of a precision stress relieved through a die kind of thing, so it's easy to machine. It's not pre-hardened or anything like that. Easy to machine relatively, but it has a lot of toughness and a lot of strength without necessarily being hard. So I thought that might be a good choice. They say it's good for shafts and things with keyways and things like that. So we'll see how it does. But it is not weldable. Like any kind of steel that's had some lead added or been resulfurized, this one's a resulfurized type steel. It's not really considered to be weldable. So how do I attach this to that shaft? This one's hardened, that one's unweldable. You know, initially I thought maybe I'll silver braze it or TIG weld it or something like that. I didn't think it was really going to work. It was just going to break, or, you know. So I made it about a 1/1000th press fit. And then I also used a Loctite 648 bearing retention compound. Super glue, basically. So we'll see. It's about 10 kilowatts, so it's maybe no, it's like 7.5 kilowatts. It's maybe 10 horsepower motor. Cross fingers. It is a 24-volt motor. So got two batteries. I'm going to try to do a soft start, if you will. So I'll either start it on one battery, or I'll start it on two batteries, but through like a stainless steel coil to reduce the speed and the current, get the mass of the engine going without really whacking a whole bunch of torque into it. I don't care if I break this, really don't care. These splines break off, you know, hey, we learned something and we'll change the design to make that not happen. I do not want to break anything in the engine. That stuff is hard to get. This, $200 starter. We can burn through a couple of these if we have to. So let's see if it holds up. I guess if it doesn't hold up, it'll just spin on the shaft, and we'll know, and we'll have to do something different. What I did not want to have to do was make this all one piece. I thought that was a little beyond my abilities at this point. Also, if it wasn't going to work in the first place, why go to all that trouble? So to do that, we would have to form internal straight splines to engage with that shaft. Don't think they're all that standard, so I don't know how we would do that. EDM or something like that. I don't even want to go there. So then we have our starter adapter that I made. This nose mounts in here like that, and then these large holes here, two of them which are hidden down there, take a socket head cap screw. So that's a socket head cap screw clearance hole. Come out the bottom, bingo bango. So this mounts on the starter, and then this slides over the studs on the adapter that's already in there. These just are some clearance holes for some nuts that are already there. So I kind of think we're ready to go. We're going to put the solenoid back on here. I'm going to mount this adapter on the starter, and then I think the starter is ready to go on the engine. Now, what we're really working towards here in the progression of sort of getting the engine running, you can see it's on the frame now, and it's we've started on the fuel tank. Started on the fuel tank. So we'll mount the fuel pump. So we kind of got fuel coming together there, and I bought some oil for the engine. It has oil in it, but I think I'm going to just replace it as a matter of course, because who knows how old that oil is. Let's see, let's get some lube for this here. Get some white lithium on there. So I'm going to replace the oil, I believe. The oil in a gas turbine engine doesn't really get dirty because it's not subject to combustion byproducts like a internal combustion engine. It's the oil is lubricating the cylinder walls, and then it's combustion and it scrapes the walls, and so you're always getting little dirty bits of crap in a internal combustion engine oil. So the oil itself is not subject to that kind of thing in a gas turbine engine, but I have no idea how old this oil is in this engine, so we'll just replace it anyway. I found a good deal on some oil. I think the oil is probably out of date per se, so it most likely couldn't be used in a like an airplane application, but we don't care. So but on to kind of the next steps. Get the starter mounted, kind of do some of the electric for the starter to kind of figure out what we need for solenoids or whatnot to engage the starter through our soft start circuit, which we still have to make. Also, we kind of need the fuel system functional to the point where we could supply low pressure fuel through our low pressure pump and filter and all that to the fuel control and high pressure pump on the engine. Now, why is that? If we're not going to try to start it yet, why do we need fuel? That fuel pump is lubricated by fuel, the high pressure fuel pump on the engine. So I don't want to do any motoring tests, that is spinning the engine. I don't want to do any motoring until we have fuel available to the engine. So even though we're not going to turn the high pressure fuel cock on, we still need to have that fuel in there to lubricate it. So we've kind of got a lot of stuff that has to come together kind of all at once. So I may do a starter engagement test before I do a real motoring test. Like I may hook up one battery to the starter and just see if it throws it out there and engages and rotates, or if it just breaks immediately, which I hope not. So we may do that because we could turn the engine over a couple revolutions. We'd probably be fine there, but One annoying thing about this, there's a threaded shaft on the starter solenoid, but there's no way for it to engage into anything to hold on to. So then you have a nylock nut that goes on there, and there's no way to hold the shaft, the threaded shaft. So you just got to kind of spin it and pull it in and out, try to get enough friction on there to get that nut to engage. There's a little cover for it. Not sure we really need that on there yet, but so I don't lose track of it. Okay, so I think we are ready now to mount the starter adapter on the starter. I've kind of marked the up point there, clocking. So by putting that there, this will be about 11 o'clock or so. So I don't know if you can tell by me struggling around with this thing, but this starter is heavy. About 45 or 50 pounds. It's no joke. I think this is probably more at home starting a 15-liter diesel than what we're using it for. That's the the original application. Oh, I guess I should mention, I bought this little tachometer. It's just like an infrared light, and it comes with some little strips of reflective tape. It just basically counts pulses. So what I wanted to know was, is this starter capable of rotating fast enough? I did some math based on what the gear reduction is at the engine. Gear reduction there, I believe, is 2.8 to 1. And I was going to need, a certain number of RPMs to start the engine and light it off. I think I needed something like 800 RPM or something like that. So I just wanted to see if, what the RPM was of this starter. Now this, of course, was unrestrained because we just put a 12-volt battery to it to see. But this starter did like 3,700 RPM or something like that. So, I know that's not, the word of truth there necessarily, because it's just not connected to anything. No load, I guess you'd say. But, if it wouldn't even do the RPM we needed on the unloaded test, we know it would never do it on the loaded test. So, these screws kind of fight a little bit going in because I made a little mistake in the bolt pattern when I was making the holes for this. So they were slightly off. I had to run a bigger drill bit through there. It's kind of embarrassing, but they do work. They just fight a little bit there at the end because they're a little bit off pattern. Oops. So, I guess I couldn't get hired at Rolls-Royce to build jet engines. All right, well, I'm going to get the rest of those fully seated and move the camera around a little bit. We'll see if we can't put this thing on the engine.